This is Free Range Digital Design Foundation Modeling, Chapter 22. Topic of this chapter is primarily registers. Registers is a very important part of another popular circuit, which is an accumulator, and we'll get into both of those in this chapter. Quick review items here, since we'll be using this with registers. Everything you can do with a bit: set it, clear it, toggle it, or do nothing with it. And do nothing is also referred to as a hold. So there's two types of digital circuits, which are combinatorial and sequential circuits. Combinatorial circuits, outputs are a function of the inputs. As a result, they have no memory. So in a sequential circuit, the outputs are a function of the sequence of inputs, which implies it needs to have some recall of the previous inputs of that previous sequence of inputs, and thus it has memory. So our basic memory element was a D flip-flop. It's a 1-bit storage element. It was similar to a latch, but the latch was considered level sensitive as opposed to a flip-flop, which was edge sensitive. So the latches are considered to be asynchronous circuits because the outputs can change anytime the inputs change, whereas flip-flops are considered synchronous circuits because, generally speaking, this changes in the outputs are synchronized with the clock edge. Two types of triggering, edge triggering on these flip-flops. It can be a rising edge or a falling edge. So this is a rising edge. Always put a rising edge trigger, and this is a falling edge. So this, the way this is drawn here with this triangle, that indicates it's a rising edge. If there were a bubble there, that would indicate it's a falling edge trigger. So pretty much everything we do in this book is going to be rising edge. The register, a generic register, is essentially an n-bit storage element as compared to a D flip-flop, which is a 1-bit storage element. Accordingly, this is a generic representation of an n-bit register, and what it is simply n D flip-flops connected accordingly. Accordingly means all the flip-flops share the same clock signal, which is right there, and then each of the flip-flops have a different data input, which is on the bottom here, and different data output on the top. These Q's right here represent these Q's. These D's represent those D's. These registers can be any width. They generally work all the same like this. Changes in the output are always synchronized with that clock edge. Once again, we can use the same type of vernacular we used before, in that this element is going to store data. We consider it as the element latches the data on the D input into the memory elements of the register. So registers are extremely important. Probably half of all the digital circuits out there are a register of some type. So let's look at that. So this is a register with load control. So this previous register had no load control, which was not very useful. So essentially what we need to do is control when that register loads or not. And we do that with this load input. And what this means is the D input can only be latched into this register if that load is asserted. And by the way it's written, it's an active high input. First of all, we have this timing diagram here, and I'm going to go ahead and mark these rising edges so I don't mess it up. Next, I have to think, well, there needs to be a initial state of this flip-flop, and I don't know what it is. The problem doesn't state it, so we do not know what that value is, and we'll just put question marks there to indicate we don't know what that value is. But what we have here is, right here, the load input's asserted, and we have a clock edge, and what's going to happen is this data is going to be latched into the register on that clock edge, and so on that clock edge, this data right here gets latched into the register. And that's going to be the same for all these. I'm going to look at this clock edge. What I see here is the load is turned off, therefore it's not going to load, therefore it's going to hold the same state at least till the next clock edge, which is fine. Notice that in between here, the D input changes, so that change is ignored. Change is ignored because the load input is not asserted. Okay, next clock edge here, we do see that the load's asserted. We got a clock edge, you got data, and that becomes 0x29. Okay, Moving forward, we see next clock edge, load's turned off, so it's not going to change state. Next clock edge still turned off. And these two clock edges, the loads are not asserted. This last clock edge here, we do see the loads asserted. Loads asserted there. Here's your data. Here's your clock edge. And here's your final data. And we will call that done. So the important thing here, summarizing, we have memory device that only latches data into its memory when that load input is asserted. And so that means that load input is necessarily a control input. These are data inputs. We're going to consider that clock a control input also. Very similar to flip-flops, typically you see registers with asynchronous inputs, and typically, most often, there's some type of clear input, which is what we have up here. But once again, when I look at this diagram here, I see a clear input, but I do not know whether it's asynchronous or synchronous. Someone has to tell me whether it's synchronous or asynchronous, and this problem happens to say that clear is asynchronous. Load is synchronous. That's all we need to know to do this problem. So it's similar to the last problem in that to make this problem work, I am going to mark these rising edges. I got to make sure I see these two clears here, not forget about them because those are asynchronous clears. Active low asynchronous clears, they are going to clear the flip-flop whenever they're asserted. So what we see here is clears is asserted, so the initial state of this flip-flop is going to be 0. At this next clock edge, we see that the load's asserted, the clock edge load's asserted, and the clear is unasserted, turned off, and what's going to happen is this 1A is going to be loaded into that register at that point. So the next clock edge here, load is still asserted, so we see the new data, which is 0xe0, loaded into that register. Next clock edge, it's still asserted. The load is still asserted, 0x29. This data latches into that register. And yet again, the next clock edge, the load is still turned on. And we get 0x35. Okay, next clock edge, load's turned off. And so it doesn't change. Next clock edge is still turned off, the data still doesn't change, but what happens at this point, the asynchronous clear is asserted, and so at this point the output's going to be cleared. Okay, one thing to notice here is when this clear unasserts at this point, the data stored in the flip-flop, which is all zeros because it was cleared, doesn't change. So the fact that the clear unasserts doesn't change the data that's being stored in the register. Okay, here is an example problem, and what it's doing is comparing 3 consecutive values and determining whether those 3 consecutive values are equivalent. Now, the idea is there's only one input on this circuit, and so let's go ahead and draw that. I'm going to be short on space on this one. Here's the high-level circuit. What it's going to do is compare 3 consecutive values of A. The values of A are going to be considered what's there when, at least the previous values, when clock input is there, and if they're equal, it's going to say so. The issue is there's only one 8-bit input, but I have to compare the 2 previous ones to that, and so what this means is I need to memorize what those 2 previous inputs were, and that means it calls out for nothing other than 2 registers sitting on this. There are my 2 registers. The other issue in this circuit is I need to compare stuff. I need to compare 3 values, and now comparators only compare 2 values at a time, so I necessarily need 2 comparators on this one. That's all I need. I know actually I need one more piece of logic in here. We'll fill that in later. So what I'm going to do is going to be comparing the input, which needs to be stored, so we'll go ahead and write that. Okay, comparing that with the previous input. And so that's the first comparison we need to do. But we need to do the more comparisons, and to do those comparisons properly, we need to store the data. So this output here is going to be latched into that second register. On any given clock edge, the A value is stored in this register, the value in this register is stored in this register. Now, those two things happen simultaneously. So the other issue in this is I'm doing a comparison of two more values. So I'm comparing these values, which is that previous value, with the other previous value. And there's my two comparisons right there. So the issue is if these two are equal and these two are equal, then the output of the circuit's going to be equal. And so that means, once again, I need an AND gate because I have to have both of these equal. This is the final output on this thing. Now, I think I'm done on this one. I usually like labeling. The last thing I do on these circuits is check them over, add in labels as I need to make it clearer, and I think this is good as done. So what controls this circuit is, I see comparators that have no control input. I see register with no control input, and I will say this has no control. Now, one issue here to notice is that I chose not to put a load input on the registers. If I had put a load input on the registers, it would have been something like this. I would have tied it high so that it's always loading. But I didn't really need to do that for this problem. It's understood that if there's no load input, it's always loading. This is a important circuit, and has its own little digital design foundation module. And so here it is. Registers, they're storage elements. They store the input data. Here's my data coming in, data coming out. This is an n-bit model, meaning essentially these n's are the same. Generally speaking, you never see different data widths between the output and input data. So these are the control inputs. Generally speaking, it's the clock. I usually have a load control, and typically or often I have a clear. Recall that this clear input can either be synchronous or asynchronous. Someone needs to tell you that. Generally speaking, it's assumed that the load input is always synchronous, and if it's not that way, someone needs to tell you that too. But generally speaking, you could always assume the load input is synchronous, and the clear input, you can't really assume. Someone has to tell you. If someone doesn't tell you, well, then you get to assume. But generally speaking, the problems should state directly. But on a good note there, that means when you're drawing schematic diagrams with registers with clear inputs, somewhere in your diagram you need to state whether the clear input is synchronous or asynchronous.